Hi people, in the last lecture we had dealt with a very nice property related to a trigonometric function being reciprocal of the other, which we had studied in trigonometric functions, but here in inverse trigonometric functions the arguments were getting reciprocated, right? So here, when now we are here meeting again, we have to start with the next property, which is property 6, and deal with it. Now what does it say? Property 6 deals with another concept. Property 5 dealt with one concept, right, and all the results in property 5 were related to that concept, which was reciprocal. Here the concept is the sum. What is it that we need to study over here? Now property 6, the result that it is going to portray is something very important and has huge number of applications. It is mostly asked in exams, like one question always has to be there from property 6. So what is this property trying to say? First let's understand that, and then we are going to talk about its applications as well. Property 6 says that specifically for tan function, if I am interested in the sum of tan inverse x and tan inverse y, where x and y are two inputs which are valid for the function tan inverse. Please always keep in mind that tan inverse is a function from collection of all reals to open interval minus pi by 2, pi by 2, and the graph that it follows, first of all let me write such that tan inverse y is equal to x if and only if tan x equals y. So if you are aware about the definition of tan, you are always aware about the definition of tan inverse, because tan inverse sends an element to x. If it is sending y to x, that means x is the unique pre-image of y under tan. Clear? That's the definition which frames the design of tan inverse, and here obviously y is sitting as the input for tan inverse, y is sitting as the output for tan, so y has to come from collection of all reals and x has to come from input of tan, that is the domain of tan, or the range of tan inverse, which is minus pi by 2, pi by 2, open interval. First thing, second thing, and the third thing is about the graph. What about the graph of the tan inverse function? Tan inverse has domain as collection of all reals and it has range as minus pi by 2, pi by 2, open interval, so this is pi by 2. Similarly there is minus pi by 2, and you have your very tan inverse function like this. Is it understood? That's the graph of tan inverse x. Fine. Once we are through with this, these are the three prerequisites which are going to be needed to do any result related to tan inverse. Right now I have to show, this is 0, I have to show tan inverse x plus tan inverse y is equal to what? Well, the result is that this is actually a branch function. That means depending upon x and y coming from where, which part of the entire real line, because x and y are inputs for tan inverse, and inputs for tan inverse can only come from the collection of all reals, because that is what is the domain. So x and y, depending upon x and y coming from which section of the real line, is going to give impact towards the result of tan inverse x plus tan inverse y. So what is tan inverse x plus tan inverse y is going to be completely dependent on the section from which x and y are coming. So we have tan inverse x plus tan inverse y is equal to tan inverse of x plus y upon 1 minus xy if x into y, this product that is written, is less than 1. Whenever x and y are coming from that section of the real line such that when you take their product it comes out to be less than 1, then for that x and that y, tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy. If your x is positive, y is positive, and x into y is greater than 1, in that situation tan inverse x plus tan inverse y is not equal to this, it is equal to pi plus tan inverse x plus y upon 1 minus xy. So if x and y are coming from that section of the real line, basically positive real line, such that their product is greater than 1, right? If they are positive, if both of them are positive and their product is greater than 1, that means what? If they are positive and product is greater than 1, in that situation, for that x and that y, tan inverse x plus tan inverse y is pi plus tan inverse x plus y upon 1 minus xy. You obtain this quantity and add a quantity pi to it. The final result that you obtain is the value of tan inverse x plus tan inverse y for x and y satisfying this condition. Cool? And if you have x less than 0, y less than 0, but x into y is greater than 1, because product of two negative quantities is a positive quantity, and it is not just positive, if it is greater than 1, in that situation you get minus pi plus tan inverse x plus y upon 1 minus xy as your answer. So if x and y are coming from that section of the real line for which x into y is greater than 1 and both of them are negative, in that case minus pi plus tan inverse x plus y upon 1 minus xy is the value of tan inverse x plus tan inverse y for this x and this y. These are the three cases which define the very three sections of the real line from where if our x and y come, then what will be the value of tan inverse x plus tan inverse y for that x and that y. Clear? So the very first thing that we have to understand is, I am going to divide this in three cases, case 1, case 2 and case 3. Okay, case 1, case 2, case 3. If I talk about case 1, case 1 says x and y are such that x into y is less than 1. Now x into y can be less than 1 provided x is positive and y is positive, even then x into y can be less than 1. X into y will be positive in that case, but it can be less than 1. Or x into y can be less than 1 when x is negative and y is negative. In which case again x into y is positive, but it can be less than 1. This can be one case. Or it can be x is positive, y is negative, in which case x into y is negative. The moment it is negative, it is less than 0, so automatically it is less than 1. Or the next is x is less than 0 and y is greater than 0, in which case again x into y is negative. The moment it is less than 0, it is less than 1. So these are the four sub cases inside case 1. That x into y is less than 1 provided x and y both are positive, x into y is less than 1 provided x and y are both negative, x into y is less than 1 when 1 is positive, 1 is negative. Okay, so four sub cases we have to understand in here. All the four sub cases are going to imply the exact same answer for tan inverse x plus tan inverse y. Clear? So let's begin the proof. This thing should be very much clear to you. We have to now begin the understanding of the proof of this result. Okay, so this will be our case 2 and I have this as less than 0 and x less than 0, y greater than 0. Let's talk about case 1. Under case 1, sub case 1. Under case 1, the sub case 1 is when x is greater than 0, y is greater than 0 and x into y is less than 1. So x into y less than 1 has already been suggested to me by case 1, but x into y can be less than 1 under this case, this case, this case or this case. So I am taking this case such that x into y is less than 1. Fine. Now see, x and y are two real numbers such that they are both positive and their product is less than 1. If x and y are positive, clearly x and y are positive real numbers, right? That means automatically they both are lying on the real line, and set of all reals is the domain for tan inverse. So tan inverse x, as it is a function from collection of all reals, to minus pi by 2 pi by 2, therefore definitely tan inverse of this x and tan inverse of this y that we have, tan inverse of this x and tan inverse of this y is going to be equal to say A and say B, such that these A and B are images of x under tan inverse and image of y under tan tan inverse. This a and b are going to lie inside this range, which is minus pi by 2, pi by 2. Minus pi by 2, pi by 2, and minus pi by 2, pi by 2. But there is a contrast. What is the contrast? See, if I talk about the tan inverse function, we had just seen the graph. How did it behave? How did the graph of tan inverse behave? At pi by 2 it is not defined. At minus pi by 2 it is not defined. This is 0, fine, and you have this as the graph of tan inverse. If x is positive, look over here. If x is positive, that means if x is coming from here, then tan inverse x is moving from 0 to pi by 2, isn't it? If x is lying here, then tan inverse x is lying here. So, if x is positive and y is positive, then tan inverse x lies in 0 comma pi by 2 open interval, and tan inverse y lies in 0 comma pi by 2 open interval. So, this a and b that we have don't lie in minus pi by 2 open interval. In fact, they lie in 0 comma pi by 2, 0 comma pi by 2 open interval. Because x is strictly greater than 0. X is strictly greater than 0. If x would have been equal to 0, in that case, my tan inverse x would have been equal to 0. Right? But because x is strictly greater than 0, tan inverse x is also strictly greater than 0. It is lying in 0 comma pi by 2 open interval. Pi by 2 as it is not included. Similarly, tan inverse y lies in 0 comma pi by 2 open interval. It is completely directly evident from the graph. Fine. So, tan inverse x is here, tan inverse y is here. Now, just understand what is, I am going to use a result for from trigonometric functions, which is going to help us get through this result. So, if you remember, what is tan of a plus b? That is the result which is going to be used over here to prove this inverse trigonometric function result. Tan of a plus b was tan a plus tan b upon 1 minus tan a tan b. That is the very result from trigonometric functions that we know. Now, if you focus upon this statement and focus upon this statement, let's come over here. Tan inverse x equals a, let me write a rule. It says tan inverse a equals b if and only if tan b equals a, provided what happens? A comes from the domain of tan inverse or the range of tan, which is collection of all reals, and B comes from the range of tan inverse or domain of tan, which is minus pi by 2 open interval. Over here, if you take this x as small a and this a as small b, you can see x is a positive real number, so definitely x is a real number, so a is a real number, and capital A is coming from 0 comma pi by 2. 0 comma pi by 2 is obviously a part of minus pi by 2, right, and therefore b is definitely coming from minus pi by 2, that is theta is definitely coming, that is a is definitely coming from minus pi by 2, and therefore I can write tan inverse a equals b as tan b equals a. This implies tan of capital A equals x. Similarly, over here, if you take this as a and take this as b, small b, then you know y is also a positive real number, so definitely y is a real number. Secondly, this capital B, which is my angle, this is lying in 0 comma pi by 2, which is again a part of minus pi by 2, and therefore b is lying in minus pi by 2 open interval, and therefore again tan inverse a equals b can be replaced by tan b equals a. Why did I write it like this? Because I want to incorporate this in this result of trigonometric functions. What is it that we can do now? What is it that we can do now? See, if I want to incorporate this in here, tan A will be replaced by x, tan B will be replaced by y, tan A into tan B will be replaced by x into y, and this will remain tan of A plus B, right? So what is it that we are going to have in all? Tan of A plus B is tan A plus tan B upon 1 minus tan A tan B, right? Now see, x is positive, y is positive, so x plus y is definitely positive. If x into y is less than 1, if x into y is less than 1, minus of x into y is greater than minus 1. So 1 minus xy is greater than 1 minus 1, which is 0. So you are getting that this denominator is also positive. Numerator positive, denominator positive, this fraction is also positive. That means tan of some angle is positive. In which quadrant is tan positive? Remember? In which quadrant is tan positive? This is first quadrant, second quadrant, third quadrant and fourth quadrant. The rule was ASTC. Here all are positive, here sin cos positive, here tan is positive, here cosec positive. So here understand, in the third quadrant tan is positive and in the first quadrant tan is positive. So if I am getting tan of A plus B is positive, if I am getting tan of A plus B is positive, this implies A plus B, that is the angle, lies in either the first quadrant or the third quadrant, because in the second and fourth quadrant tan is negative, lies in first or third quadrant. A plus B lies in first or third quadrant. Now, see where was A lying and where was B lying. Remember the range of A and B? A was lying in 0 comma pi by 2, B was lying in 0 comma pi by 2. So if A is greater than 0 less than pi by 2, B is greater than 0 less than pi by 2, then A plus B is greater than 0 plus 0 less than pi by 2 plus pi by 2, which is pi. So A plus B is lying between 0 and pi. In the first quadrant, angles range from 0 to pi by 2. In the second quadrant, they range from pi by 2 to pi. In the third quadrant, from pi to 3 pi by 2, and in the fourth quadrant, from 3 pi by 2 to 2 pi. So obviously, if my A plus B is only ranging from 0 to pi, it has to lie in first or second quadrant. It cannot lie in the third, it cannot lie in the fourth, because then it will be exceeding its very measurement of pi. So A plus B can lie in either first quadrant or second quadrant. Right now we have A plus B definitely lies in either first or third, but it cannot lie in third because it only ranges from 0 to pi. It is not exceeding pi. For lying in the third quadrant, it should have measurement exceeding pi. So it cannot lie in the third, and because it can lie either in first or third, and we have finalized it cannot lie in the third, that means A plus B is lying in the first quadrant. So this implies A plus B lies in first quadrant. So understand, first step was to make sure which are the two quadrants, one among which A plus B is lying in. And then we crossed out one because A plus B's measurement was only from 0 to pi, so third quadrant got cancelled out, we finalized the first quadrant. So A plus B therefore is lying in the first quadrant. This means A plus B is greater than 0 and less than pi by 2. Alright. A plus B is greater than 0 and less than pi by 2. Fine, it cannot be 0 because tan of A plus B is not equal to 0, it is greater than 0. Tan 0 is 0, you know. So A plus B has to be greater than 0, and obviously at pi by 2 tan is not defined, so it cannot be equal to pi by 2 because tan is defined at A plus B, but tan is not defined at pi by 2. So here equality cannot come, here equality cannot come, so we have A plus B lying between 0 and pi by 2. If A plus B is lying between 0 and pi by 2, what can I now next say? See, what did you have over here? This is what you have. So you have tan of A plus B is x plus y upon 1 minus xy. This quantity is a positive real number. And this angle that you have is lying in 0 comma pi by 2 open interval. That's what we have. Now it's time to recall a result which says, I just wrote tan inverse A equals B if and only if tan B equals A provided what happens? A comes from the domain of tan inverse or the range of tan. What is the domain of tan inverse? Collection of all reals. And B comes from either the domain of tan or range of tan inverse, which is minus pi by 2, open interval. Here you can see if I take this as small b and I take this as small a, small b right now you can see is coming from 0 comma pi by 2 open interval, which is a part of minus pi by 2 open interval. So clearly a plus b is coming from this set. So small b is satisfying this very condition. This quantity small a has to be a real number. I know this is a positive real number. If it is positive real number, then definitely it is a real number. So set of all positive real numbers are part of real numbers. So a is also satisfying this condition, and therefore tan b equals a can be replaced by tan inverse a equals b. What is it that we are going to have then? We will be having nothing but tan inverse a equals b. We will be having tan inverse a is what? X plus y upon 1 minus xy equals a plus b, right? But we have written capital A is tan inverse x and capital B is tan inverse y. So I can write capital A is tan inverse x, capital B is tan inverse y. This is equal to tan inverse x plus y upon 1 minus xy. Tan inverse x plus tan inverse y is equal to tan inverse x plus y upon 1 minus xy. And this is the proof. We have proved the very first case for the first subcase. If x and y both are positive real numbers and x into y is less than 1, then tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy. This is about subcase 1. If I talk about subcase 2, how will my situation change? Let's see. If I talk about subcase 2, how arguments are going to differ, how things are going to differ, but still because I want the same result, how eventually I am going to get the same result. This we have done. Chances of this, subcase 2. Second subcase is that x is negative, y is negative, but x into y is less than 1. This is the second case. Now again, tan inverse x and tan inverse y, tan inverse x and tan inverse y. I can apply tan inverse on this x and y. They are real numbers at the end of the day. They are negative real numbers, but what's the problem? They are real numbers. So if tan inverse is being applied to x, it is going to create an output, and it is going to create an output here as well. Where will a and b lie? Obviously in the range of tan inverse, but somehow there is a specification. What is the specification? Specification is this, that this is pi by 2, this is minus pi by 2, this is 0. That's the graph of tan inverse x. Right now we have x is negative. Previously we had x positive. If x is negative, that means x is lying here. It is strictly negative, so it is not equal to 0, okay? If x is negative, you can see tan inverse x is ranging from minus pi by 2 to 0. If x is lying here, tan inverse x is lying here, okay? Similarly, y is lying here, tan inverse y is also lying here. Because x is not attaining the value 0, tan inverse x will not be equal to 0, so it will be strictly between minus pi by 2 and 0. So we have, if tan inverse x is capital A, tan inverse y is capital B, this capital A is definitely going to lie where? Because x is negative, capital A, that is tan inverse x, will be lying in minus pi by 2, comma 0. This will also be lying in minus pi by 2, comma 0. Fine. Now what is it? We had just recently did that. If tan inverse x is a, where x is a real number and a is coming from minus pi by 2 open interval, this is a part of minus pi by 2 open interval, right? It's a part of minus pi by 2 open interval. In that situation, we had done that tan of a plus b, which is equal to tan a plus tan b upon 1 minus tan A tan B. This is equal to what? Tan A plus tan B. Tan of A will be equal to x, tan of B will be y upon 1 minus xy. Now understand, this is a real number. What type of real number? X is negative, y is negative, so x plus y is negative, and 1 minus xy is positive because xy is less than 1. Numerator negative, denominator positive, clearly this is negative. So we had just done that tan x, tan function, this is the first quadrant, second quadrant, third and fourth. The rule is ASTC. Tan is negative in the second and tan is negative in the fourth quadrant. So if tan of A plus B is negative, this implies A plus B lies in either the second quadrant or it lies in the fourth quadrant. But it does not lie in the first and it does not lie in the third. Now which among these two is the final quadrant in which A plus B lies? That is going to be coming from here. A is greater than minus pi by 2 less than 0. B is greater than minus pi by 2 less than 0. So this implies A plus B is greater than minus pi by 2 which is minus pi, and 0 plus 0 is 0. That means A plus B lies in third or fourth quadrant. From minus pi to minus pi by 2 is the third quadrant, from minus pi by 2 to 0 it is the fourth quadrant. This says A plus B lies in second or fourth, this says A plus B lies in third or fourth, that means definitely A plus B is lying in the fourth quadrant. A plus B lies in the fourth quadrant. Therefore, A plus B lies in fourth quadrant. This means A plus B is actually ranging from minus pi by 2 to 0. Fine. We had tan of A plus B is equals to x plus y upon 1 minus xy. I just said that this is a negative real number, and we have that this is lying in minus pi by 2 comma 0. Just recall the result again, that tan inverse A equals B if and only if tan B equals A, provided A comes from collection of all reals and B comes from minus pi by 2 open interval. If I take this as small b and take this as small a, I am getting that small a is a negative real number, in which case definitely it is a real number. So small a is lying in collection of all reals, small b is lying in minus pi by 2 comma 0, which is definitely a part of minus pi by 2 open interval, and therefore small b is also satisfying this condition, and therefore by using this result I can write tan b equals a as tan inverse a equals b. I can write this as tan inverse a equals b. So this implies tan inverse of x plus y upon 1 minus xy equals a plus b. What is a plus b? Capital A was tan inverse x, capital B was tan inverse y. So this is nothing but tan inverse x plus tan inverse y. So we have got the exact same thing. Tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy, provided x is negative, y is negative, and x into y is less than 1. For all x negative, y negative, x into y less than 1. So that proves our subcase 2. Right? If x is positive, y is positive, and x into y is less than 1, then for that x and that y, tan inverse x plus tan inverse y is this. In fact, even when x is negative and y is negative and x into y is less than 1, even then tan inverse x plus tan inverse y is the same very outcome. That means what is playing the role is this. It is this which is at most important. From wherever x and y are coming, as long as their product is less than 1, all the time the answer of tan inverse x plus tan inverse y is going to come out to be this only. provided x into y is not less than 1, it is greater than 1, then my answer is going to change like this or like this. But if x into y, the product you have to take of the arguments, if that comes out to be less than 1, your answer is fixed, which is this. Clear? If it is not less than 1, if it is greater than 1, then that's a different story. Okay, we are going to talk about case 3, case 4 and all the rest of the cases as well, and the sub cases left in the next lecture. So, I will see you then. Thank you.